Hello, this is going to be video 2 in the dynamics video series. This video is going to be on the time derivative of position, velocity, and acceleration, but without using chain rule. If you want to see the chain rule video, that's going to be the next video. This one is going to be without chain rule. So, when talking about the position, velocity, and acceleration relationship, it's important to note that based on what you learned in lecture, velocity is just the first time derivative of position, and acceleration is just the next time derivative of velocity. So you can think about it like this. So if you have position, you can take a time derivative. So first time derivative, I'm just going to put TD is velocity. And then, the next time derivative, so another time derivative of velocity, is going to give you the acceleration. Right. So, knowing that, we can start the problem. So we have a function of position given in the time variable. So we have x as a function of time is 3t squared plus 5t minus 10. The first part is going to ask us to evaluate the velocity when t equals 2. So what we're going to do, first we're going to write down this position function. So we have 3t squared plus 5t minus 10. And since we know that the velocity time function is going to be just the first derivative of the position function, we can just take the first time derivative here and get that velocity as a function of t is going to be, recall how to take a geometric derivative. So we're going to go first term. That's going to be 6t plus 5 minus 0. So that's our velocity function. We can solve part A immediately now. When we know that t equals 2, then this becomes velocity at 2 is equal to 6 times 2 plus 5. And then solving that, we'll get the end result is 12 plus 5, or just 17. Right? So velocity as a function, velocity at time equals 2 is going to be equal to 17. Now we can evaluate the acceleration. To do that, we need the acceleration as a function of time. And to get that, we can just take the next time derivative of velocity. Right? So acceleration is going to be the next time derivative of velocity. So we're going to examine that first term. 6t becomes 6 plus, and then 5 is 0, and then 0 again. We can just omit that. So knowing this, since at acceleration when time is 2 is what we're looking for, that's just going to be plugging a 2 wherever you see a t. In the acceleration equation, we have no t's, so it's just going to be 6. And that's our answer for acceleration. Okay, so this second problem is a little different. In this one, we're not actually given position, we're given acceleration. And we want to work backwards towards velocity is what it's asking for. So given that our function for acceleration with respect to time is 6t minus 4, we have to figure out that given that at time equals 2, velocity is 5, we first have to determine the constant of integration here. So we're going to be integrating this function to get velocity, and then what is the velocity at t equals 0. So that's undetermined yet. So our first step here is recognizing that the acceleration function, we want to go backwards and get to velocity. So how do we get from acceleration to velocity? If you remember, when we went from velocity to acceleration, we did a derivative. And so the backwards of a derivative, right, to go from acceleration to velocity, we're going to integrate. All well and dandy, but let's actually see how it's done. So we know one thing, and that the velocity as a function of time is equal to the integral of the acceleration as a function of time with respect to time, so dt, right? Write that a little nicer. Yes. Moving on, we also know that acceleration as a function of time, which is that at portion, is also equal to 6t minus 4 in this top part dt. Yes, onward. So from here, we can just do the integration power rule, which is working backwards. So you remember for the power rule, we multiplied the exponent by the coefficient and subtracted 1. In this one, we're doing kind of the reverse order of that. So we're going to be first adding 1 to the exponent. So this exponent is 1 right now for the t function. So when I do that, I'm going to add 1 to it. So it's going to be t squared, right? And then we're going to be getting our coefficient and dividing it by our new exponent. So 6 over 2. All right. And then that 4 just becomes a 4t. Right. We're going to simplify this a little bit. So 6 over 2 is just 3. T squared minus 4t. And then since this is an indefinite integral, we have to also add our integration constant, so plus c. Okay. So we want to figure out what c is in this case, and how can we do that? So we're actually given a couple things. So we can actually rewrite this whole thing as the velocity equals 3t squared minus 4t, just to make it a little more truncated, plus c. All right. And we actually are given an initial condition. So if you recall up here, they said that given at t equals 2, the velocity is 5. You have to determine the integration constant. So we can plug these values in for t and v in the equation we just derived. So we know that v equals 5 here. I'll make that in blue. And that equals 3 times 2 squared minus 4 times 2 plus c. Now we can just use our algebra skills here to solve for c. So I'm going to move these two other terms to the other side. So I'm going to get that c is going to be equal to 5 plus 8 minus 12. Right? And then from here, we can get that c is equal to, what is this? 13 minus 12, or just 1. So that is going to be our answer for C. I'll rewrite it down here. Awesome. But now we want to know the velocity when t equals 0. So that'll be our next step. I'll do it over here. So at t equals 0, we want to figure out our velocity. So we now know our c and we now know our t. We can use this formula that we came up with up here again, right, to solve for our v. So let's do that. So v is going to be equivalent to our 3t squared minus 4t plus c. And we're going to plug in our given values. So v equals 3. So we know t is 0. So there's going to be a 0 there. Squared minus 4 times 0 is t. Plus our integration constant, which we just solved to be 1. So a 1 here. And then this all evaluates to just v being equal to 1 at time equal to 0. So that's our other answer for part B. That's going to be the end of this video. Bye.